The title of my speech is Benny-Luke type integral differential equation with two definition conditions at the end of the time interval. My name is Tursun Yuldashev. I am from Uzbekistan. I work at Tashkent State Transport University. In this my talk, we consider this type integral differential equations. Here, omega and nu are parameters. Omega is positive parameter, nu is non-zero real parameters, and kernel QTS is degenerate kernel. Here, the systems of functions AT and BS are linear independent. And they are also continuous functions. In solving this problem, in this equation, we use different type equations, conditions, and final type conditions. We use this condition number 2 because we seek the solution is Fourier series by sinus, and here phi1 and phi2 are redefinition functions. They are unknown functions too. And to find these functions, phi1 and phi2, we use these additional conditions, number 4. And the choice of conditions 3 and 4 with the final and intermediate data are due to the fact in practice it is not always possible to determine the initial condition. For example, when studying the technological process of aluminum production, before the start of the production cycle, the raw materials passes through firing, and the state of the raw material by the beginning of the production cycle is not known. And the final expected state of the output will be unknown in reality. We find it from a known intermediate state, so we have an inverse problem to solve the equation 1. The main unknown function we study in this class, we take from this class. Redefinition functions are continuous functions. And we note that the direct problem 1, 2, 3 is a unique solution for all values of the parameter omega. And the inverse problem is a unique solution only for some values of this parameter omega. In addition, the second parameter mu also plays an important role in the study of solvability. This Fourier series, this is form we use to build the solution of our problem. Here, v and x is this function, and this function form complete system of orthonormal eigenfunctions in the space L2. Using this Fourier series, we obtain this countable system of differential equations. Here, tau by tau, and we denote this integral, here unknown function, so this quantity is unknown too. And we are solving this equation 9, and we obtain this presentation of solution. Here, A1, A2 unknown functions, And to find these functions, we use condition number 3. To use condition number 3, we take derivative from this function number 9 and use condition number 3 at this form. UNT is V1 and U derivative. NT is V2N. Condition number 11 and 12. And for coefficients A1 and A2, we obtain this system of algebraic equations with respect to A1 and A2. To solve this system, we consider main determinant of this system. This determinant is 1, not 0, so we can find A1 and A2 from this system. They are functions 14 and 15. And we obtain these integral equations. Integral equations with respect to Fourier coefficients of main unknown functions U and T. Here U and T. But here we have unknown quantity. To find this unknown quantity, we use our denotation, but here these functions are continuous functions, and they Fourier series with these functions converges. And to find this tau n, we substitute this function into our denotation and obtain this system of algebraic equations. The right-hand side of this system is the sum of 3 quantities. Third quantity is consists of unknown functions here. Sigma 3 in this form. And we solve this system. To solve this system, we consider this matrix, and the first column determinant must be non-zero. We consider equation delta n equal to 0, and we solve these equations. This equation is equation with polynomial with respect to this quantity of the degree not higher than k. So this equation has real roots for every value of n, and we denote them by this letter mu l. And for these values of nu, for these values, this determinant is 0. No, for another values of the parameter nu, this determinant is non-zero. Here we obtain two sets. Lambda 1 is such values of parameter nu in which the determinant is 0. In this case, our direct problem has infinite number of solutions, but inverse problem has no solutions. At the set lambda 2, the direct problem has unique solution, but inverse problem for some values from this set has unique solutions. For some values from this set has infinite number of solutions. In solving this algebraic system of equations, we obtain his solution. In this form, we solved the system by Kramer method, and the solution we substitute into function 16 and obtain this in functional integral equations. Unknown functions here on the sign of integral, and unknown function is here on the sign of determinant. And here, phi1 and phi2 are unknown functions, so we first must find these functions are quantities, these are Fourier coefficients, these Fourier coefficients from redefinition functions, functions. And to find these quantities, we use additional condition number 4. To use additional condition number 4, we write Fourier series, and we calculate derivatives from this Fourier series and use condition number 4 and obtain this system of algebraic equations. This system will solve with respect to phi1 and phi2. To solve this system, we first consider main determinant. If the main determinant is non-zero, then we can solve this system. So we consider main determinant of this equation. It has the form, this form. It will denote by V0n, formal number 26. This function we wrote in this form is equation. And this equation has infinite number of solutions. Here we see the solutions, values of parameter omega, in which this equation has solutions. And also the set of solutions with respect to omega we denote by this letter I. And here we obtain two sets. Lambda 3 is the solutions in which this determinant is 0. And the set lambda 4 in which this determinant is non-zero. Here we consider the values of omega in which this values of main determinant is difference from 0. In this set, we solve our inverse problem. In the set lambda 3, our problem has infinite number of solutions, but in the set lambda 4, our problem has unique solutions. So we find coefficients, Fourier coefficients of redefinition functions. Two redefinition functions. J is 1 to here from this set. and this Fourier series for redefinition functions. But here we see unknown functions. So first we solve equation with respect to main unknown function un. Then the values of the solution of this equation we substitute here, put here, and obtain the values of this function, redefinition function. So this representation we substitute into equations 20 and obtain finally this equation. Here only one unknown function, un. There is no another unknown functions. To solve this equation, to prove one value solvability of this equation, we use this space B2 as this norm, and we use smoothness conditions. This function from this class, and for this function, for Fourier coefficients of this function, there is this formula is true. And base cell inequalities here is true. We use this formula 31 and this inequality 32 in proof solvability of all to the system of functional integral equations. We suppose that these conditions are fulfilled. Rho is less than 1. Then this equation has a unique solution in this space, and the solution can maybe found by this approximation. First, we estimate zero approximation for these Fourier coefficients. We use these representations from formula 31, and then we use formula 32 and obtain that zero approximation is finitely. Here we use the inequality of Schwarz, Cauchy-Schwarz inequality, and we use base inequality and obtain this estimate. Then we estimate force difference. Here, to use Cauchy-Schwarz inequality, we must have the production of two Fourier series. First Fourier series is this, and second is this Fourier coefficients. And these functions are bounded. This function is bounded functions, and we assume that this is bounded. Here, this function is bounded, and we have here two Fourier coefficients, lambda(n) and 2n. Here we use Cauchy-Schwarz inequality and obtain this estimate, and this is known from our estimate 34. So this is finite, and we estimate arbitrary difference by this way, and obtain that this difference is less than this one. Here, rho is less than one. So the operator on the right-hand side of countable system of functional integral equations, so T is contracting. It follows from estimates 34 and 35 and 36 that there is unique fixed point, which is solution to countable system of functional integral equations, so T, in the space B2. And second theorem is that the Fourier series 29 is converges. Converges. This Fourier series for redefinition functions. We use estimating method 34 and 35. Obtain that this function is finite too. And we estimate this Fourier series for mean unknown function. And it is not difficult because we have necessary estimates 34 and 35. So this function is convergence. So there is this theorem. If the conditions of the theorem 1 are fulfilled, then the main unknown function 2tx of the inverse problem 1, 4 is defined by the Fourier series 38, and this series converges absolute and uniform in the domain omega for all values of values new omega from this set. And the function 38 belongs to the class, this class. To prove that this function belongs to this class, we take derivatives and using formula 31 and 32, we estimate this Fourier series using this formula. So I finished my speech about these remarks I told you. Thank you very much for your attention.